Hello, this is Math 2231 coming to you from the College of DuPage for summer 2020, and this is a continuation, another continuation of our lecture To Infinity and Beyond. Alright, so today we're going to consider the end behavior of a function over an infinite interval. This is what you called it in pre-calc. But it really is letting the end, we're saying what happens way out here as x tends to infinity, or way out here as x tends to minus infinity. So as x decreases without bound, or x increases without bound, you see from the numbers that this expression for f of x approaches 3 either way. And so that means there is what we call a horizontal asymptote. And so we would write the limit as x tends to minus infinity of f of x is equal to 3. And we'd also could write the limit as x tends to positive infinity of f of x is equal to 3. And so this statement means that the limit exists and the limit is equal to L. Now in this case the limit exists because L is a real number in this discussion. We define that, and it's defined rigorously in terms of epsilons, and this time we don't have deltas, but we have capital M's and N's. And again, epsilons and deltas and capital M's and N's are not the focus of this course, although you will be tested on them. You can get a good grade. We're not focusing on this, we're focusing on other things. So here's the definition of limits at infinity, and what this means is f of x gets close to L eventually. And for minus infinity, eventually it gets close. And that means it stays within epsilon of L as you get bigger and bigger. And as I said before, this is what we call a horizontal asymptote. And so you can have a horizontal asymptote as you tend to minus infinity or plus infinity. And we will see examples where these are actually different. And so a function can have at most 2 horizontal asymptotes. Here's a theorem, and you can prove this using epsilons, m's, and n's. So if r is a positive rational number, you might want to think about what happens if it's negative. But if r is a positive rational number and c is any number, this limit is going to be 0 because that's a fixed number in the numerator. And also this number is going to be 0, whether you go to plus or minus infinity. Think about that for a while. And in fact, why don't you think about it while you're doing this this problem? You know what to do. Let's see how you did. And the answer is 5. Pretty straightforward use of properties of limits. Here is another problem, and this is finding this limit as x tends to infinity of, now I have 2x minus 1 over x plus 1. And again, you can't, well, I shouldn't say that. We'll talk about it. Let's see how you do. Let's see how you did. Well, you can't just plug infinity in, because infinity isn't a real number, and you get an indeterminate form. Before we talked about 0 over 0 being infinity, 0 over 0 being an indeterminate form. Here, infinity over infinity is also an indeterminate form. But the technique that you can use here is you can divide top and bottom by the same thing, and we're dividing by x equals 0 in each case. And we see if we divide the numerator by x and the denominator by x, we've really multiplied by 1 in a clever way, resulting in this. And now we can use the theorem that we have to say that this is going to end up being 2. So you see, here's the picture, and again, you see this is a horizontal asymptote. It approaches from underneath the horizontal asymptote as you go to positive infinity, and it approaches the horizontal asymptote from above as you go to minus infinity. You might note that this problem also does have a vertical asymptote as well. Okay, so then we come to this. Here are 3 problems for you to do, A, B, and C. You know what to do. And in fact, we're going to let this be the end of this, and after you do the work, see me in 11.